experiment that we're flying is really building on a set of experiments that was done maybe a decade ago on the crystallization of colloidal atoms. And this is a situation where one looks at a colloid as a model atom because it's relatively large, relatively slow, and it's something we can visualize the kinetics and the structure of that we can't do for atoms. What we're doing now is based on things that we've done here at the Colorado School of Mines over the last decade, where we've used applied fields, optical fields, electrical fields, even magnetic fields. We're trying to extend these to the fabrication of colloidal molecules, so from atoms to molecules. And these are very complicated, if you will, structures that better model polymers, proteins, amino acids, things of that nature. And our hope is that we can study the kinetics and structure evolution in those systems once again, as was done on the space station before. At Earth gravity, sedimentation and convection and these sorts of forces influence the structure formation in ways which don't allow us to form crystals. And this is really what we're after. You can try to density match these systems, so use a fluid that's the same density as the colloid, but that won't work for systems like systems that are colloidal molecules, which are formed of colloidal atoms that are of different density. And so, since we've gone to much more complicated systems where we have this colloid of this density and this colloid of this density, we can't simply density match those systems. And so we need to do these in space or in microgravity environments in order to make them realizable. To get the experiment manifested, we responded to an NRA from NASA and basically got funding for a long enough period of time to both do the fabrication, get the experiment designed, and then eventually to fly it in space. The application process was straightforward. I think it was well reviewed, and in the end we're getting great assistance in terms of how we are going to make these experiments actually function in space. One of the unique advantages of the experiments we propose is the use of electric fields. And the E-field experiment is going to allow us to directly manipulate and effectively control nature in a way that's going to allow us to tune the crystallization and control the kinetics of the processes we want to study. When we run the experiment, we expect to see both what we expect, which are some of the crystallization and kinetics associated with simple crystallization. But we also expect to see interesting features that are going to arise due to the complex nature of the molecules we're assembling. So once again, these are polymeric long-chain linear structures. These are structures which are chiral, and we expect to see very unique features that we're only going to be able to observe in space. Personally, what's most exciting to me is that over the course of the last 10 years or so, we've developed techniques which are quite unique, and these have to do with electrical manipulation, optical manipulation, and even magnetic manipulation of particles for other applications. And this is primarily in biomedical applications. But we're now going to be applying them in very fundamental ways at these fundamental studies of crystallization and crystallization kinetics in a way that we've not been able to do before because of the constraints of gravity.